Hi everyone, welcome in this new series of lectures on implicit regularization, Benign interpolation, and Benign overparametrisation. The topic for today will be implicit regularization that I will explain. So first, here I give you some references. So these are the main references for this lecture. And as always, you have the lecture notes that you can find on the web page, whose link is provided in the description of the video. So before explaining all this topic, let me give some motivation for looking at them. So very classical theory tells you that you have to find a good balance between bias and variance. Okay, so if you look in any textbook, what you will find is the following. So first of all, you can decompose the risk as the sum of a bias term and a variance term. And now, if you look at the complexity of the model, so for example, you can think to the number of parameters in your model. When you increase the complexity of your model, you will have more and more flexible models. And for this reason, you will have a bias that will decrease because you will be able to have a better approximation. But at the same time, when you increase the complexity of your model, you will have a variance that will also increase. And this is due to the fact that you will be more and more able to interpolate the data, and so you will be more and more able to capture all the noise. All right? So the classical figure that you have in your textbook is that if you look at the risk, which is the sum of the bias and the variance, it should be the sum of this curve on this curve. So you end up with this smiley curve. And what it tells you is that if you have a low complexity, then you will have a large bias, so you will have a large risk. So you underfit your data, which is due to the large bias. And when you have a large complexity, you will have a large variance. So you will have at the end a large risk and you will overfit the data. So the best is to be somewhere in between here, where you have the best trade-off between the bias and the variance. So the bias is not too large, the variance is not too large, and this is the complexity of the model that you should choose. So this is really what you find in any classical textbook. But now there have been some empirical observations which are somewhat different. So this observation essentially comes from people fitting neural networks. And most of the time they fit very, very complex neural networks or very complex model without any regularization, and they observe the following. So as long as the complexity is small, so smaller than the ability of interpolating the learning data, they have this smiley curve as before, but beyond the interpolation point, so when they interpolate and they add more and more complexity to the model, so complexity in neural networks means more and more neurons, more and more layers, then they observe that there is this descent and the variance decrease beyond the interpolation point. So this phenomenon is known as a double descent phenomenon, and the goal of this series of lectures is to explain this part of this diagram. So there will be 4 videos. The first video, the video of today, is on implicit regularization of gradient descent. The second video will be on Benign interpolation, and I will essentially give some intuitions. The third video will be on the mathematical analysis of Benign interpolation, and the last video will be on overparametrization. So let us start with our topic, which is implicit regularization of gradient descent. Sometimes you may find implicit bias of regularization, but I prefer the name implicit regularization because bias has a very specific meaning in statistics, and this is not what we are talking about. So we start with the simplest model. So we'll consider a linear regression and a Gaussian even linear regression. So we have n observation of a linear model. So we have some yi that you observe, which is a real number. And this yi is given as the scalar product between some covariates xi that we also observe, and some vector beta star that we don't observe, plus some epsilon I, where the epsilon I is a Gaussian noise, which is IID with variance sigma 2. So here what we don't know is the coefficient beta star of the linear regression. So as usual, we will write it in the vectorial form. So denote by capital Y the vector of the yi, yn. The same for epsilon. And we consider the matrix capital X, where for each row, we will set each observation x1, xn. Okay, so you have this classical y is equal, okay, so we can do y is equal x beta star plus epsilon. Okay. So if you are looking at this Gaussian linear model, maybe you want to do some maximum likelihood estimation. And what is the maximum likelihood estimator in this case? It is simply the least square estimator, because the negative log likelihood is equal to this plus some additional term that does not depend on beta. So essentially all you need is to minimize this. So this is the least square problem. So very classical. And now we consider the high-dimensional regime. So if I am in the high-dimensional regime with a number of parameter p, which is the input dimension larger than n, then what we have is that if you look at the dimension of the kernel of x, so it is equal to p minus the rank of x, and since the rank of x is always smaller than n and p, so it is smaller than n, p minus the rank of x is always larger than p minus n, which is strictly positive. So the dimension of the kernel of x is strictly positive, which means that there are an infinite number of solutions to this problem, because you can add anything in the kernel to one of the solutions. So this is the first remark, and now we consider not only this high-dimensional regime where we have no unique solution to LS, but we also consider the interpolation regime where the rank of x is exactly equal to n. Okay, so you know that it is always smaller than n and p, and we assume that it is exactly equal to n. And this is typically what will happen when you have in a high-dimensional setting where p is large. So when the rank of x is equal to n, then what you have is that you have solution to y equal to x beta. So the minimum here of your least square problem is achieved at something that interpolates the data, where this is equal to 0, right? So if you take any solution of the least square problem, it is equal to this equation. So it means that for any data point xi and yi, you have that your predictor evaluated at xi is exactly equal to yi. So you exactly interpolate the data on the learning dataset. So I think that you have learned that interpolating the data is maybe not a good idea because this may lead to overfitting. So is it a good idea? So first, let me explain what is so recall, I would say rather, what is the usual practice. So usually what we do is we consider this term, and in a high dimensional setting, what we do is that we will add a penalty. So for example, you may add the ridge penalty, where you simply add lambdas times the norm of beta square with some lambda which is strictly positive. And when you do this, you end up with an objective function which is strictly convex. So first of all, you have a unique solution. And because of this penalty, you have some beta that will have a solution that will have a norm which is not too large, though this will avoid very bad behavior by fighting against a too large overfit. But what happened is that there is a recent practice in neural network where people don't add any regularization. They just do plain gradient descent or stochastic gradient descent on the objective, and they use the solution that is selected by gradient descent. So the question is, okay, so we look at the a zero-order neural network, which is just linear regression. So if you look at this problem of linear regression, when you want to do a least square, what is the solution if I just do gradient descent on this? So look at this problem. So we look at this function, and we do gradient descent started from 0. So if I want to do this, I first have to write one iteration of gradient descent. So what is an iteration of gradient descent? It is given by this formula. Okay, so I take my beta hat and then I do a gradient step. And what you can do is an induction. And if you do an induction, by using the fact that you start from 0, you end up with this formula after t plus 1 step of gradient descent. Okay, so this is a simple exercise. You can check it by yourself. And now if you look at this matrix, if eta is small enough, so eta must be smaller than 1/2 of 1 over the square of the operator norm of x. So in this case, you have that this matrix will converge to this matrix. And what is this matrix here? This is the Moore-Penrose pseudo-inverse of the identity minus 2 eta x transpose x. Okay? So I remind you that Moore-Penrose pseudo-inverse just means to take your matrix, do SVD, and invert the singular value of the SVD and switch the left and right singular vector. So for a reminder of Moore-Penrose pseudo-inverse, you can look at the lecture notes in the appendix C. So for this convergence, you just have to write the SVD and see that it converges like this. So again, this is a simple exercise that you can do by yourself. So at the end, if you look at this matrix, so it looks a bit ugly, but it simplifies because here I have identity, here I have identity, so both of them will simplify. So at the end, I just have 2 eta x transpose x plus, and here I have 2 eta x transpose. So all this simplifies. Again, just look at the SVD, and you end up by just having x plus y, where x plus is the Moore-Penrose pseudo-inverse of x. All right, so what we have seen is that if you do gradient descent on the least square started from 0, you end up with a solution which is simply x plus y. So now the question is there anything special with this solution? Does it have some nice or bad properties? And it turns out that this solution is very special and it has a very nice property. So when you are in the interpolation regime, I remind you that it means that rank of x is equal to n, then what you have is that this solution, so it is interpolating because you know that in this case you have solutions that interpolate the data. So any solution, any minimizer of the least square criterion must interpolate the data. So it is interpolating the data, but among all the betas that interpolate the data, it will select the beta with the smallest norm. So what you can see is that by doing a gradient descent, you select a specific interpolating solution, which is a solution which has the smallest norm. So this really corresponds to a regularization effect of gradient descent. So let me prove this result. So it is very simple. So first of all, since the rank of x is equal to n, I have that x plus is equal to the identity. So x plus y is equal to y. Okay. So x plus y, I remind you, this is my estimator. So what I have is that my estimator is interpolating. So it is not a surprise. And since this is an interpolating solution, now I know how are the interpolating solution. They are equal to this solution plus anything which is in the kernel of x. Okay, so you can describe all the interpolating solution of y equal x beta, so any solution of y equal to x beta, by x plus y plus beta 0, which is in the kernel of x. So the second point is to notice that the range of X transpose and the range of X plus are the same. And why are they the same? Just because, again, you look at the SVD. What is the difference between X plus and X transpose? Just you take the singular value and you take 1 over the singular value. So you take the SVD of X transpose, yes, and you take 1 over the singular value and you get the SVD of X plus. So since you know that the range of X transpose plus the kernel of X are in direct sum and they span all Rp, you will have that Rp is equal to the orthogonal sum of the kernel of X on the range of X plus. Right? So you can decompose any beta in Rp as something the kernel of X plus something the range of X plus. So in particular, here when you look at this decomposition, these two terms here are orthogonal. Okay? So since here I have two terms that are orthogonal, I will have, just by Pythagoras, that the square norm of beta is equal to the square norm of the term which is in the kernel of X and the square norm of my least square estimator selected by gradient descent. So just by looking at this formula, you see that the beta, which has the smallest norm, is the beta for which I have only this term, and this term is just equal to 0. Okay? Because I have that this norm is always smaller than this. So my estimator here that has been selected by doing gradient descent on this square minimizes the norm among all the solutions to y equal to x beta. So this is the first example of regularization by gradient descent. So now we look more briefly to another example, which is for logistic regression. So we move from a regression setting to a classification setting. So now we have some labels, while I, that will be -1 or +1. So we are in a binary classification setting. And we will do some regression and use as a predictor the sign of beta hat scalar x. Okay, so we predict with this sign. And how we will learn beta hat, we'll just apply some gradient descent on the empirical logistic risk. So the empirical logistic risk, we just take the average of the logistic loss of yi beta scalar xi, where I remind you that the logistic loss is given by this formula. So L of minus z is equal to log of 1 plus exponential minus z. Right, so when you do this, you are just doing a simple logistic regression. And what we will do, so we will do some gradient descent on this objective function. And again, we want to focus in the interpolation regime. So what will be the interpolation regime? It will be in the case where when you look predictor like this, and you apply it to the learning data, you apply it to the xi, you will recover exactly the yi. Okay, so it means that you are able to separate linearly your data, your xi, yi, by some hyperplane. Okay, so we consider this case, and we consider gradient descent on this logistic class. So you apply your gradient descent, so this will decrease, and since you can separate your data, you can imagine that after some steps, t, you will be able to perfectly classify the training data, which means that if you look at your regression, it will have the same sign as your labels. Okay, so if you take the sign of this, it will be exactly equal to yi. So you interpolate your data, but you have no reason to stop here. You can still do your gradient descent in order to have a smaller loss. So let us look at this quantity. So the first thing that you will do is to just observe that here you have something which is linear, so it is homogeneous. So you can rewrite your loss by simply multiplying and dividing by the norm of beta hat t. Okay, so why do we do this? Because here you observe that you have something which is strictly positive, all right? And in addition, your loss is decreasing. So since your loss is decreasing, what you can do is to just send this quantity to plus infinity. And since this is positive, all of this will go to 0. Okay? So you can send your loss to 0 just by sending this to infinity without changing this. Okay? So you can imagine that gradient descent will send the norm to infinity in order to have the loss going to 0. So let us assume that this norm is going to infinity, which looks natural. And now we'll use the fact that if you look at your logistic loss here, actually when z goes to infinity, this is equivalent to exponential minus z, right? So you can approximate here the logistic risk by this quantity where I have replaced the logistic loss by the exponential function. Okay, so now you know that if you take the sum of some exponential with something that goes to infinity and some coefficient here, the only term that will remain in your sum when this quantity goes to infinity are the term for which this is the smallest. So essentially, what you will have when you will do your minimization, you will have here something that will be essentially equal to, you will only keep the term for which this is minimum. So you will have the exponential of your term that goes to infinity and the minimum of these terms here. And how many terms do you have like this? You have n min term like this, and you have over n because you have a 1 over n. All right, so what you see is that you have a loss which is essentially proportional to this quantity. So you have a term here that goes to infinity, and you have another term here. So what you can imagine is that gradient descent tries to go to 0 as fast as possible. So you can imagine that gradient descent will try to make this quantity as large as possible. Okay, so it makes sense to believe that if you take your gradient descent and you look at the direction given by your gradient descent, it will try to maximize this quantity. So it will try to maximize, take the maximum over all possible direction, what is called the margin of the classifier, which is the minimum over I of yi u scalar xi. So here I have several times I tell you, okay, imagine that at some point you are able to perfectly classify the data, and yes, it is meaningful to believe that gradient descent goes to infinity, and it is meaningful to believe that the direction will maximize margin, and it is eventually what occurs. This has been proved by Soudry et al. In 2017. So if you look at your normalized solution of gradient descent on the empirical logistic trees, it will converge to the max margin classifier when your data are linearly separable. So again, you see that gradient descent select a very specific solution, and this solution is the solution that maximizes the margin. So the take-home message so far is that when interpolation is possible, gradient descent tends to select some specific interpolating solution. So for L2 regression, it is the minimal norm interpolating solution. And for logistic regression, this is the max margin solution. And this is what we call the implicit regularization of gradient descent, or implicit bias of gradient descent. So here I only give you two examples on linear regression or logistic regression. So is it something which is more general? Yes, it is. And this is something that we can generalize to more complex model, even if it is a bit harder to describe precisely what's going on. So I will not give too many details. But for example, if you consider some neural networks, And you train some neural networks that will be homogeneous. So for example, you take a neural network with ReLU activation without any bias term, and you use the logistic loss. Then, if the normalized weights converge, what you see is that at the limit, they will solve the max margin problem. So you see that this kind of result can be generalized to a more complex model, nonlinear, very highly nonlinear, like neural networks. So that's all for today, and what we will see in the next video is what is the statistical benefits of having this implicit regularization for least square. So see you later.